hopefully you've had a chance to try this problem. It's a big one and challenging. I'm going to walk through the solutions now. So if you haven't given it a try, please pause and do it now. So in this problem, we're asked to draw a cooling curve of methanol. All right. And to calculate the amount of energy that'll be absorbed or released by a 2.75 gram sample of that methanol gas as it cools from 77 degrees Celsius all the way down to negative 97.6. And it's a solid. Now, you note that the melting point that's given is 97.6, negative 97.6 as well. So that means that's going to go through that phase transition of freezing and then stop once it's a solid. So let's draw this curve first, and then we'll dive into the calculation itself. So I've got my temperature right here. My heat is being removed because as things cool, they're going to decrease their amount of kinetic energy on average. So we're actually going to have this sample release heat into their surroundings. So we're going to be removing heat from it. So we're going to start up high at a high temperature at 77 degrees Celsius. That's where we're going to be starting at. And we're going to cool this gas until we hit the boiling point, which is going to be 64.7 degrees Celsius. So a boiling point is also the same as a condensation point. It's just the phase change of vaporization or condensation. Both phase transitions will occur at that same temperature. So it's going to be a gas, then it's going to go from a gas to a liquid. And then once it hits, everything's become a liquid, it's then going to decrease again until it hits the freezing point, which is the same as the melting point because both freezing and melting takes place at that same exact temperature. And that's going to be at our negative 97.6 degrees Celsius. And then at that point, we'll have freezing take place until we have everything as a solid, and then things will begin to cool some more. But we're actually going to stop right there. We're not actually going to look at this at any lower than this freezing point. So we're going to go here. So we're going to go all the way through that that freezing phase change. And so here's the cooling curve that we're looking at. Now, for each of these sections that I'm going to highlight green, we're going to use our equation for Q, that Q equals mass times specific heat times that change in temperature, where change in temperature is the final temperature minus the initial temperature. And our freezing or our specific heats will be different for the gas versus the liquid phase. And we've been given two different ones. So we've been told that the specific heat for the liquid is different than that of the gas. And we've been given those two values. Then for the phase changes right here, where we're going from the gas to the liquid, and then from the liquid to the solid, we're going to be using our enthalpies of, so when we go from our gas to our liquid, we're going to be condensing. So we're going to use our enthalpy of condensation, which is equal to the negative of the enthalpy of vaporization because it's the opposite of that phase change. And then for the last phase transition, we'll be using the enthalpy of freezing or crystallization. Just a super long word, which is really equal to the negative of the enthalpy of fusion because it's the opposite. All right, so that heat of fusion we've been given right here. So that actually means that the enthalpy of crystallization is going to be equal to the opposite of that. So my enthalpy, so for this part right here, my enthalpy of crystallization, I'm going to abbreviate that XTL. It's an old habit. It's my abbreviation for crystal. Will be equal to the negative 3177.3 kilojoules per mole. Now, for my enthalpy of fusion right here, or sorry, not fusion, my apologies, condensation, I don't have that given to me. I don't. Instead, what I have are vapor pressures at two different temperatures. So I'm going to use those to calculate my enthalpy of condensation. I'll calculate the enthalpy of vaporization from it, and then the opposite of that will be my enthalpy of condensation. So these values right here can be used to calculate the enthalpy of vaporization. So this will be multi-stepped. So let's dive into it. Let's go ahead and start with our enthalpies for our phase transitions, and then we will do the enthalpies for our gas and our liquid phase. Or sorry, not our enthalpies, our heats for our gas and our liquid phase. So let's look at the first one, the trickiest one. Let's start with the enthalpy of condensation and the heat that is required to be released during that process. So to calculate this, to calculate the Q for our transition going from our gas to our liquid, we really want to multiply the number of moles of our ethanol by that enthalpy of condensation. So we have to calculate both of those things. Right. So first, the number of moles, that's going to be equal to my mass, 2.75 grams, times the inverse of my molar mass of methanol, which I calculate from my periodic table, and it is going to be 32.04 grams per mole. And that's going to give me a value of 0.0858 moles of methanol that I can use in my calculations, both for that condensation and for that freezing phase change. Okay, so that'll come in really handy. In fact, it's going to come in so handy, I'm going to highlight this so we can easily find it later. All right, so now let's figure out this enthalpy of vaporization. I'm going to use the Clausius-Clapeyron equation once again. So I'm going to abbreviate that CC equation because it's such a long thing to write. So if you remember, that's going to be the natural log of my higher pressure divided by my lower pressure. So I've got, and before we use millimeters of mercury, as long as you're using the same units for pressure, it doesn't matter which units you use because the units are going to cancel anyway, right? It's just a ratio. So we're going to have 0.5263 atmospheres divided by our 0.1285 atmospheres. That's going to be equal to the negative of our enthalpy of vaporization divided by our R value. And R is 8.314 joules per moles Kelvin. And that's multiplied by the inverse of our two temperatures, the difference between them. So it's always the second temperature minus the first temperature, as long as that second pressure is on the top of our natural log ratio. So that's going to be 50 degrees Celsius, which I'm going to convert into Kelvin first. So that'll be 273 plus 50, which will give me a value of 323 Kelvin. And I'll subtract then my 20 degrees Celsius converted into Kelvin. So 273 plus 20 is going to give me a value of 293 Kelvin. Big equation. Takes a minute to plug into my calculator and solve this, but I got a value for my enthalpy of vaporization that's equal to 36,979 joules per mole. That is going to be equal then to my enthalpy of if that's my enthalpy of vaporization, my enthalpy of condensation is the opposite. It's negative 36,979 joules per mole. All right, so now I have the information I need to actually calculate the heat that is going to be released during that phase change. So we're going to have, this is going to be equal to, let me give myself a little bit more room, 0.0858 moles times that negative 36,979 joules per mole, which gives me a value of negative 3,172.8 joules. All right, well, that was a lot to get through the first one. So that's going to be for that phase change that goes from gas to liquid. So now let's take a look at what happens when we go from the liquid to the solid. Now we already have a heat of fusion, so this will go a little bit faster because we already have moles. We don't have to calculate the enthalpy of fusion. So the heat to go from a a liquid to a solid is going to be equal to the number of moles times our enthalpy of crystallization. Now, that enthalpy of crystallization is equal to the negative of the enthalpy of fusion, which is given to us. So it's going to be equal to negative 3,177.3 kilojoules per mole. So to calculate this in terms of joules, I'm going to set this equal to the number of moles I calculated that I have for my 2.75 gram sample times that enthalpy of negative 31773. And I'm going to convert this into joules since all my other calculations are going to come out into joules. I'm going to add these all up at one point. And so this is going to be equal to, or times 1,000 joules divided by 1 kilojoule, giving me a value at the end of this calculation of, it's a big one, negative 2726123 joules. Whew. And that corresponds then to that liquid transitioning into a solid. So I'm halfway through. I've got 2 of my calculations done for my 2 phase changes, but I still need to calculate the heat that's released when I am cooling my gas and the heat that is released when I'm cooling my liquid. Right, so I've created a little bit more space, but I've saved the values that we just calculated for the heat absorbed for both of our phase transitions. Now let's start with the heat that's absorbed for a gas, and then we'll look at a liquid. So for the gas, we're going to be using our equation that Q is equal to mass times specific heat times the change in temperature. And we're going to make sure that we're using the specific heat for the gas and not the one for the liquid. So plugging this in, we're going to use that 2.75 grams. And then the specific heat in the gas phase is the 1.632. So I'll multiply that by 1.632 joules per gram degrees Celsius, and then multiply this by my change in temperature. So for my gas phase, I'm starting at 77 Kelvin and I'm cooling it until I hit the boiling point where it's going to start condensing at 64.7. So my final temperature is 64.7 minus 77 degrees Celsius. And I should get a negative number here because I'm cooling it. I should see a decrease in my temperature. And that'll give me a negative value for my heat, meaning that heat is going to be released rather than absorbed by this system. All right, just plugging this into my calculator, I get a value that's negative 55.2 joules. Great. Now I need to do the same process for the liquid. So the heat for the liquid, again, using the same equation. So here's gas, here's liquid. It's going to be equal to that 2.75 grams times, this time the specific heat is larger. It's 2.48. So it takes more heat to cool the liquid, or it releases more heat as it cools the liquid than it would the gas. So that's going to be my 2.481 joules per gram degrees Celsius. And I'm then going to multiply that by the change in temperature. Sorry, my cat just laid on my computer in front of me. It's hilarious. So I'm going from that 64.7 degrees Celsius all the way down to negative 97.6. And the negative 97.6 is going to be my final temperature. So I start with that and subtract the 64.7, which will give you a large negative value, but that's a large drop in temperature. And plugging this into my calculator, I get a value that is negative 1,107 joules. All right, so now I have everything I need to calculate my final total amount of energy that is released by my system. And remember, this is cooling, so it's an exothermic process. It's going to be releasing heat. All right, so basically I'm just adding these values up. That's all I'm really doing to complete this problem. So the heat released, it's going to be my negative 3,172.8 plus my negative 2726123 joules, plus my negative 55.2, which seems so insignificant compared to the last number, plus that negative 1107.3 joules. All right, adding that all up together, I'm going to get a value that's negative. I'm going to round this to just 3 significant figures based on my mass, 3 sig figs, and my melting and boiling point. I realize my vapor pressure at 20 degrees and 50 degrees Celsius is 1 sig fig. I'm going to assume it's more just so that way we can give you a few more values since it was just pulled from a table. So this is going to give us negative 2730. And I can report this in joules, but it's such a big number, I might choose to report it in kilojoules and have this be negative 2,730 kilojoules that's actually absorbed. And that is the solution to this big problem.